We're going to be working on part 1 today, and then we have a homework due tonight over part 0, which I'm also going to discuss in my notes because there's some weird stuff in there. So this particular module is about forecasting, and essentially what's going to happen is we're going to be looking at these predictions that were made by a previous class several years ago, and essentially trying to determine how accurate and how consistent they were in their predictions. And we'll sort of define those things as we go along. Today, we're going to be looking at consistency of these 4 events. And in my notes, I will talk about what that means in a second. The spreadsheet looks something like this. We got 3 tabs along the bottom. All of part 1 is with this data here. It's just a small set to get us started so we can figure out this stuff. But then as we move further into the module, we'll go into this larger data set, essentially doing some of the same things as before, just with more complicated data. So that's what we're up to in this module. If I move over to my notes, the first thing I want to talk about today is what we are doing in part 0, because it tends to be something that some people aren't super familiar with. So I wanted to talk about it. So part 0 is about something called summation notation. And all it is, it's just a way to write out certain types of math that just makes it easier. So like, for example, if I wanted to write out the sum of the numbers from 21 to 30, you'd have to write it like that. You have to, write all 10 numbers in there and add them up. This is doable, but you can obviously imagine, if it was, what if it was 21 to 99? It'd be really annoying to write out all those numbers. So instead, we have this notation that means the exact same thing, and it's obviously a lot quicker to write. So let's talk about what's going on in each of these symbols here. This giant weird symbol is a capital sigma, and essentially it means we are going to start adding some stuff up. Specifically in this case, the X on the right side of the sigma tells us what the things look like that we will be adding up. And then along the bottom of the sigma, it tells us not only the variable that is changing, but it tells us the first value that we're plugging in, and the number on top tells us when we're going to stop. So for example, on this example here, the things we're adding up all look like x minus 1 squared. And so we have like 3 of those things over here. And as you can see, we replace the x with a 2. So that's our first value that we're plugging in. And we keep repeating this process with plus signs in between until we get to 4, because 4 is the number on top. So that is how you would expand this notation here and write it out as an expression that you can actually solve and get a number for. So how I would do this in Excel would be the following way. Let's say we had this example where now we're adding up 9 things. So we have 9 terms in this summation. It's really obnoxious to have to actually write out all 9 things. So we want to, try to use the dragging benefits of Excel as much as we can. So this is what I would do. I would first write out a column of all the possible X values. And then I would write out the formula for the first term, except instead of X, I obviously just reference the first term in my left column here, so that when I drag, it automatically becomes a 3 and a 4, etc. And the number I'm actually interested in would then be at the bottom, where I add up these 9 terms. And so really, this column here, you can drag, this column here, you can drag. It's sort of 2 different things, and a third formula allows us to do all 9 of these terms sort of quickly, so that we're not having to waste time writing all of them out. Now, There is one more type of example that tends to throw people off in the homework for part 0, and it looks like this guy. This guy actually has two variables. We have an x and then this little I that's smaller than it and sort of down to the right. This is called a subscript, and it's not a normal variable where like it doesn't mean x times I. When it's this little term over here in this little lower right area next to the x, which is what a subscript is, think of it as a label. So that's the first x plus the second x plus the third x. It's not x times 1 and x times 2. It's a label of which x we are using. And the reason this is helpful is like sometimes you have like 30 variables and you don't want to have to go through the entire alphabet and say, okay, well, this one's A, this one's B, so on. And so sort of a lazy way to label them is say, okay, they're all X, but this one's the first X, and this one's the second X, and so on and so forth. And so in this summation notation, the variable that's changing, which is on the bottom of my sigma, is I. So I have X1 through X4, and then you reference some table that tells you what these are, plug them in, add them up, and then you're done. So it's just a little bit more different when you get to that example there, but it's essentially the same. So that's what you're going to be doing in part 0 today, if you want to give it a shot. It's not too bad once you get the hang of it. Now, what we're doing in part 1 is something called consistency. And essentially, it has to do with, do these predictions make sense? So let's talk about probability first for a little bit. Let's say I have a classroom filled with people, and every single person in this classroom is between ages 18 and 21, and I know exactly how many of each there are. If I wanted to say, like, if a person is chosen at random, what's the probability that they're 18? Well, this is actually very easy to compute because I have all this information. I just say, oh, there's 10 18-year-olds out of 40 people. So 10 out of 40 is there's a 25% chance that I'm going to pick an 18-year-old at random out of this room. Well, that is not quite what we're doing. What we're doing is actually more like this. I have no idea how many of each group are in this room. So it is more of a prediction. It's a it's a guess that we're making. There is no right answer initially. So if I asked you to make a prediction about choosing a person at random that's 18, and I said, what do you think that is? And you said 20%. That's fine. It's just a number you make up essentially. You don't have any more information. So there isn't really a wrong answer initially, as long as it's between a 0 and 100. You can't say there's a 150% chance. That doesn't make sense. But what I want to talk about now is what happens if we make multiple predictions. Because if you make multiple predictions, then you can be wrong, or what we say here today, you can be inconsistent. Here's an example of how that works. Let's say person's chosen at random, and I say that, oh, well, there's a 20% chance that that person is either 18 or younger. But then I make a second prediction. I say, okay, I'm still choosing a person at random out of the entire planet. I think there's only a 10% chance that they're 19 or younger. That doesn't make sense. You're implying somehow that there are somehow less people that are 19 and younger than there are 18 and younger. That's not possible, because if you are 19 and younger, then you're also already, no, I had that backwards. If you're 18 and younger, you're also already 19 and younger, but not vice versa. So like this entire group of people is contained in the second group, but the second group has even more people, the 19-year-olds, in addition to that. So that's a larger group. It should be more likely that you choose a person at random that's in the larger group. So what we're doing here is essentially identifying subsets, and we say that a group of people whose age is 18 or less than or equal to 18 is a subset of a group of people whose age is less than or equal to 19. Now, just because 19 is the larger number doesn't necessarily mean it's the larger group. I can actually reverse the direction of these inequalities, and the opposite is true. For instance, if you consider everyone in the world who's 18 and older versus everyone in the world who's 19 and older, now the 19 and older is the smaller group because the other one contains all of those people plus more. And so in that case, it's the opposite relationship. Now, 19 and older is the subset. So first thing I want to talk about is how do you figure out which one is the subset? Because sometimes it is confusing. And one way I like to sort of think about it in my head when I'm trying to figure out which one the subset is, you can say, well, if the subset happens, or if you're in the subset, then you're necessarily also in the larger set, but not the other way around. So like, for example, if you pick someone at random that happens to be 19 or older, you already chosen someone who's 18 and older, but not the other way around. And because of that, the first group, the ones who are 19 and older, is a subset of the other one, of all the people who are 18. Now, why is this important for us? What does this have to do with probability? Well, when you're making predictions, the probability of the subset occurring is always less than or equal to the probability of the larger set occurring, right? If there's this small group of people, it can't be more likely that you choose the smaller group than the larger group. Then the last thing I want to talk about that has to do with this probability stuff is one more sort of rule. Let's say we make another prediction about choosing a person at random who happens to be 18 and younger, and we say, okay, it's 30%. Well, if we do that, and then we go to make a second prediction about, okay, well, there's a 30% chance that someone's 18 and younger. Well, that forces our prediction for choosing someone at random who's 19 and older, who would have to be, 70% in that case, because there is 100% chance that one of these two things happens. Either you're 18 and younger or you're 19 and older. There's no other possibility. And so these predictions sort of have to add up to 100%. And that leads us to our second rule, where if you have two or more sets where one of them is guaranteed to occur, and only one of them can happen at the same time, these things have to add to 100%. Okay, what does that have to do with what we're doing in this module? Well, when you open the spreadsheet for part one, you are going to have this group of predictions. So there's these 12-ish made up people that made predictions about the weather tomorrow. So this first person said, I think there's a 20% chance that it's going to snow at least an inch or more tomorrow. And then they also made a prediction that they think there's a 10% chance that it snows 5 inches or more tomorrow. What your job is to go in here and say, like, compare, two of these predictions next to each other and say, does that make sense? Is it consistent? And in my opinion, the best way to do it is essentially by creating new columns, kind of like what we did last module. And we say, okay, like, did they meet their goal? I'm going to put a 1 or a 0 here if they did. Same thing. You can say, are these pair of predictions consistent? And then you can put like a 1 or a 0 if they are. And then you can make another column comparing like these two predictions. That's another question involved in part one. But that's the basic idea. You're just looking at this and essentially determining if they were consistent, which is a fancy way of saying, do those predictions make sense? And for part one, all you have to do is check those two rules we just talked about. And so like, to start, the very first question is going to ask about these two things. So what you're going to do to start is say to yourself, which of these two events is a subset of the other one? For example, if it snows an inch or more tomorrow, is it guaranteed to snow 3 inches or more tomorrow? Or is the other way around? If it snows 3 inches or more tomorrow, is it guaranteed to then also have snowed 1 inch or more tomorrow? One of those two statements is true. And that kind of tells you which one is the subset and therefore which probability should be greater than or equal to the other one.